Today we shall discuss about the power consumption issues in an embedded system. What are the components which are involved really in power consumption? What are the parameters which can be dealt with to manage the power consumption will be our topic of discussion in today's class. So, why power is important? Obviously, the fundamental point is electricity consumption costs. And if we are talking about a battery powered embedded system, then that affects battery life. I would like to have longer battery life, and obviously that is the reason why I would like to optimize my power consumption. But at the same time, there are lots of other issues which are related to power consumption, because there are possibilities of failures if the power distribution is not properly managed on the silicon in which the hardware is implemented. So, what are the power consumption and problems? In fact, the power delivery, packaging and the cooling costs, and as the temperature increases, the effect of noise also becomes more dominant. So, it will be always desirable to minimize power consumption. This has also implication in terms of compaction density and reliability, because there can be spots which may be heated on the chip itself, and that may lead to failures. So, a particular point of consideration here is that of power density, that is how much heat is getting dissipated over the chip area, and this is typically measured in the unit of watts per centimeter square. Power is not in general distributed evenly over the chip. So, a failure can happen if really there is a spot which is highly heated up. In fact, silicon is not a good heat conductor. With high power density, we also cannot assume in a sense power uniformity. So, if you have high temperature, that may lead to high leakage of the current, okay, and high power, and that is leading to high temperature. So, it becomes a kind of a loop. Okay. Now, the hot units are those units in the silicon area which actually are widely used, which are being densely used, and there the power consumption would be more, and there also there may be more dissipation, and the temperature at those points may actually increase, and those are actually your hot spots. So, one issue in terms of design, in terms of real VLSI design, that you would like to look for a layout that separates the hot units, typically the hot spots, okay, and that can increase what is called processor's power envelope. What is power envelope? The maximum power that can be dissipated via cooling technologies. Okay. So, if that is more distributed, so the power envelope can actually increase. In fact, this hot spot, why this hot spot arises? Because if you look at from another consideration, you would like those units which are likely to talk to each other frequently to be placed close together, okay, for the purpose of efficiency. The moment you place them close together, obviously what happens, since they are being used intensively, the energy consumption over that area may be more, that is the temperature over those areas can actually increase. Okay. So, a basic objective of a layout in a power aware layout would be to have a smart layout, so that the hot units are distributed evenly over the chip area. Now, bigger systems will cool better and dissipate more power. But the moment I am trying to make the system smaller, which is an objective in terms of our embedded systems and embedded processors that we are looking at, we would like maybe a video camera to fit into a palm itself. So, in that case I am packing in more circuitry onto a single SoC. Okay. Then obviously the cooling possibilities gets reduced. Okay. So, you have to optimize on the circuits as well as other parameters related to the circuits, so that this power dissipation is much less. And average power density is what is most significant. So, obviously uniformly distributed power allows for higher CPU dissipation, and that is again I pointed out earlier also, that is a motivation of the layout. So, this power dissipation is what is related to therefore reliability of the system, okay, as well as that of battery life if it is operated via battery. So, how do you measure this power consumption? The simplest thing is power. All of us know that energy by time, if this is the dimensionality of the unit. So, this is how simply the power is measured. There are other parameters. This one is average power versus peak power. Depending on the activity, the peak power may be much more than that of the average power. Then you have got, we have already looked at power density, okay, which particularly is a measure to understand what would be the reliability in terms of the heated points on the chip area. So, that is power density. Ideally, it should be uniformly distributed. The other factor is what is known as energy delay. Okay. So, how is energy delay is calculated? So, energy, if we define energy E as energy per instruction, so this would be watt per MIPS, because I am having, this is the rate at which the instructions are getting executed, okay, and the delay is a time per instruction. Okay. So, if I take it, it would be 1 by MIPS. So, energy delay product, the unit would be watt per MIPS square. Now, these are the typical curves. Okay. What you find here is that if I look at the energy, VDD or VCC is a supply voltage. Now, if the supply voltage increases, obviously your energy increases in terms of your picojoule. Okay. And if you look at the delay, interestingly delay reduces. In fact, this is a phenomena, and this we shall look at in the context of CMOS, what exactly the relations that has been suggested. And because of these phenomena, you would like to look at it as a one quantity, what is called energy delay product. Now, why this energy delay product is important? Because it tells you that if you are really reducing VDD, and if that reduces energy consumption, then you may need to pay in terms of efficiency, the time taken for execution of the code. So, if you want to look at this trade off together using one measurable unit, then you use energy delay product. What are the sources of power consumption? See, dynamic power consumption is obviously charging and discharging of capacitors, because any bit transfer with regard to your MOS and CMOS circuitry finally boil down to charging and discharging of capacitors, and this depends upon what is called the basic switching activity. In fact, this is also related to the power consumption in memory, because you know the DRAMs are nothing but capacitances. This is also related to your interconnect power consumption, because on the line, transmission line also, there will be the capacitances which needs to be charged up. Second source is short circuit currents, because short circuit paths between supply rails during switching, when really the transistor switches, then there is a short circuit current between the supply rails, okay, and there that would be peak current flow in, and that would be also a source of power consumption. The last point is leakage current, that is leaking diodes and transistors, that is even when it is not switching, there will be a current leakage through these diodes and transistors. So, in a circuit, these are the basic components and the sources for consumption of power. So, there is obviously a trade-off in terms of power versus speed. So, what we say, in order to achieve high performance, we need to put all the components that frequently talk to each other as close as possible. Okay? Highly active components produces high power. Close high power components would cause hot spots. Hot spots cause high leakage that increases again the temperature. Okay? So, we need to reduce maybe the frequency to lose performance in order to keep within the thermal constraints. So, this is the basic relationship, basic conceptual relationship between components which are determining your efficiency as well as power consumption. How the power consumption is calculated in a CMOS circuit? Okay, this is the expression. Okay. Alpha is a measure of switching activity. CL is a load capacitance, because primarily the switching is what consumes power, and what we are ignoring completely the leakage component of the power consumption. VDD is a supply voltage and F is a frequency. This is a relationship of power consumption in CMOS circuits. Now, what is interesting to note is that decreasing supply voltage reduces power consumption quadratically, because the relationship is squared. And you can understand why that becomes an issue for designing efficient, power efficient and power aware architectures. At the same time, if you look into delay for CMOS circuits, that is the tau, tau is given by this parameter where Vt is threshold voltage and Vt is substantially less than VDD. Okay. Now, obviously what it shows you is that reducing supply voltage will increase the runtime of algorithms only linearly, okay, because your tau is linearly dependent on your actually VDD really, okay. And if it is very small, it becomes inverse relationship, because this is VDD, effectively it is becoming VDD square. Now, high level architectural issues with this background, now we need to look at high level architectural issues, because different applications or phase of applications can have different needs, okay. And different architecture or components of architectures do different things and have different power efficiencies, okay. Now, obviously we need to exploit this fact to make my power consumption optimal. And the other point that we have seen, that relationship of power consumption with voltage and efficiency with voltage. So, depending on computation needs, can we play with voltage and the frequency? Okay. So, all these issues therefore have to be looked at in an integrated fashion for the purpose of having power efficient architecture for embedded systems. So, how are the CPU power saving strategies are implemented? The first thing is you reduce power supply voltage. The moment I reduce the power supply voltage, power would go down. I have already seen from the CMOS relationship. Run at lower clock frequency, that is also another way of reducing the power. The relationship has already established that. The other thing is disable function units with control signals when not in use, because the high level architectural issue is that not all units will be used for a computation, okay. And disconnect parts from power supply when not in use. In fact, disable is one aspect and disconnect is completely putting it to sleep, okay, parts of the architecture. So, these becomes more from the high level issues and these more from the circuit level perspectives. Therefore, what we have as mechanisms called gating for controlling power. First is clock gating. Deactivate the clock to unused registers. If the registers are not being used, deactivate the clock, so the power consumption disappears. So, if I have a floating point unit, then registers in floating point unit can be deactivated when you are doing really integer operations. Next thing is signal gating. Deactivate signals that cause activity, okay, if not used. So, address or data buses for non-memory instructions. So, when it is not being used, I can deactivate and effectively I can save energy over there. Then power gating is actually deactivating a VDD for unused hardware blocks. Okay. So, FPU for integer program, and in this case what I have done, this clock gating I had stopped the clock, but the VDD supply is still on. So, there would be leakage current. If I stop the VDD to those registers, then leakage current is also minimized. But obviously, when I am doing a power gating, there would be higher recovery penalty. What does that mean? More time required to recover to active state. So, CPUs, by making use or combination of these gating modes, provide multiple power modes. And these modes are typically controlled by software or user. The trade-off is power saving versus speed of resuming, because you can save the power, but you have to pay for in terms of the time taken to resume active work. The generic modes that you find in many of these CPUs are what are called idle mode, nap mode, sleep mode. Idle mode, where the clock distribution is turned off. So, this is basically a clock gating. Nap mode typically is caching turned off, your cache memory is put to off, and typically this is in relation to your on chip cache mostly. Sleep mode is turn off power to unused processor logic. Okay. So, it is more of a power gating. Okay. In caching turned off, if I have to do the caching turn it off, I have to do signal gating. So, dynamic power management, because these power modes have to be controlled by the software, the user. So, what does dynamic power management therefore implies? When a device becomes idle, it can transition to lower power usage state. A fixed amount of additional time and energy are required to transition back to active state when a new request for service arrives. What is the best time threshold to transition to sleep state? Because this is the key question. Because you can put the processor to different modes or you can put different hardware components of the processor or an SoC to different modes, and that is a decision of the controlling software. Now, at what point of time, on the basis of what objectives this decision be taken? So, it says what is the best time threshold to transition to sleep state? Too soon? You pay startup costs too frequently. You may save more power, but you are not saving in terms of time, you are paying in terms of time. Too late, maybe spend too much time in high power state when you are not really using it. So, what we say, it is a kind of a thumb rule that generally transition to sleep state when cost of being in active state is at least the cost of waking up. So, that balances out the two things. If it is not so, then there is no justification for doing a mode switch. So, your software, controlling software, has to make these estimates before taking these decisions. So, let us take some example of processor where these modes are available. First example is PIC. We had studied PIC. So, PIC has got, to conserve power, a sleep mode. In sleep mode, oscillator circuit is turned off and the device actually stops executing code. You cannot really execute code on that device. However, active watchdog timer will increase the amount of current drawn. If the watchdog timer is on and it is monitoring, it will continue to draw current. And in fact, you can have timers which may be driven by external clocks, okay, which can be used for operations even when the processor is in sleep mode. So, in fact, this is a very simple architecture where you have identified only sleep mode to conserve power for the processor. Power PC we have not studied really, but that is another example of a processor which is targeted for embedded applications. Why we are looking at it? Because it has got a number of these modes: doze, nap, sleep. These are different kinds of modes with different functionalities. And what are the features? It uses static logic and not really dynamic logic. Can shut down unused execution units, that provision is provided explicitly. And the cache, okay, is organized into sub arrays to minimize the amount of active circuitry when a cache access is taking place. In fact, this point we shall discuss when we look at the memory architectures for power optimization. The interesting thing is these statistics for PowerPC. This is, we are looking in the context of PowerPC, but this is true in general across other processors as well. This, it says that percentage of time units are idle for the spec integer of floating point. These are some standards, okay, standards for evaluating the performance of the processor, okay. It's a benchmark programs. So, the spec int is for integer computation and spec fp for floating point computations. Now, you see that how the percentage of time these units are idle varies. It's the most glaring example is this one. When you are doing actually a integer computation, 99% of time your floating point ALU and registers will be unused. And if you put the power completely off, if you do the VDD off to this part, then your leakage current is definitely minimized. Okay. Now, you have also, you will see that these cache, data cache, and this is instruction cache, which we have already seen in the context of Harvard architectures. So, they are also not always used. So, about 30% of the time, okay, in case of this kind of benchmark is unused. Okay. So, here also the issue comes up how you can effectively organize this cache so that you can minimize this kind of energy consumption at this point. Next issue comes up is, obviously I had already talked about the power down costs. Going into a power down mode costs obviously time as well as energy, and I told you obviously that it must determine if going into a particular mode is worthwhile. And what is interesting is that to study this phenomena, we can model CPU power states with what is called a power state machine. So, we are looking at now an ARM variant called strong ARM, and with respect to this strong ARM, we shall have a look at the power state machine. This processor takes two supplies. VDD is a 3.3 volt supply and VDX is 1.5 volts. It has got three power modes: run, which is normal operation; idle, here it stops CPU clock with logic still powered on, this is clock gating. Then you have got sleep, shuts off most of chip activity, takes 3 steps, each about 30 microsecond, and wake up takes greater than 10 millisecond. Okay. So, these are the 3 modes for the strong arm. Now, these are the 3 also states. If I talk about power state machine of the processor, we also have these as states. So, this is the power state machine of this strong arm. Now, this is run. So, when you run in the normal conditions, the typical consumption is about 40 milliwatt. Okay. And in idle state, it is about 50 milliwatt, and in sleep mode, it is 0.16 milliwatt. Therefore, if you can intelligently switch between the states, what you really get, you can really gain in terms of power consumption. So, what is the other thing that is being shown here? Typically, it is the time that takes for transitions. The transitions both ways, from run to idle or idle to run, it is of the order of 10 microsecond. From idle to sleep and run to sleep, it is order of 90 microsecond. Okay. And from sleep, you can only go back to the run with consumption of about 160 milliseconds. So, this delay is substantial. So, whether you would put a processor to sleep or not, it has to be a staged decision, okay? That if there is really, you do not expect much activity in near future, then only you should put the processor to the sleep. This power state machine we have seen with in relation to the strong arm, but these kind of state machines can be drawn for any processor which supports multiple power modes. In fact, this state machine is actually to be used by the controlling software, which in many cases would be the operating system to decide about the different states in which the processor should operate based on maybe the load as well as the usage pattern. And there are other strategies also by which, even without involving OS, this power switch in of different states, switching into different states, power states can be done. Next, we shall look at this concept of what is called dynamic voltage and frequency scaling. The basic concept is consume as much as you need, okay? So, use lowest frequency that achieves the performance target. What does that mean? If you are using the lowest clock frequency, obviously the time taken for execution of an instruction increases. But if you really do not want a performance better than a particular time period or a threshold, you would not like to use higher frequency, because higher frequency can mean higher power consumption. Also, the same thing is related to the lowest VDD that allows desired frequency, okay? And this is can be also regulated by software based on system load. So, this is known as dynamic voltage and frequency scaling. We shall look at an example to understand this phenomenon. Let us consider we are talking about a hypothetical processor which supports 3 voltage levels 5, 4 and 2.5. And the energy consumption per cycle, which is being given by in nanojoule, is 40, 25 and 10, okay. They correspond to the different power supplies, and the corresponding frequency at which it operates are also different for different supply voltages. You operate at 50 megahertz when it is 5 volts. If the supply voltage is reduced, then you operate at a lower frequency, and as you reduce, the cycle time obviously increases. Let us consider a task, okay, which may have started at this point, which is 0, and has got a deadline of say 25 seconds, okay. This is the deadline for the task. Now, if this is the deadline of the task, what does that mean? The processor should operate in a way such that the task is finished before you cross the deadline. Now, this is one policy, or the philosophy could be complete task as soon as possible. So, if I am using that policy of completing the task as soon as possible, I shall be operating at highest voltage and highest frequency. So, it takes say this much amount of time to complete the task. So, it says that the task takes 10 to the power 9 cycles at 50 megahertz. So, if it takes at 50 megahertz, what is the energy consumption? It is 40 joule, okay, and this is calculated by this formula, okay. So, I am finding that I can finish off the task in 20 seconds if I am really using the processor at the highest voltage and highest frequency. Let us say that I would like to do this job using 2 voltages and not 3, then what happens? So, the whole thing was that whole operations requires what? 750 plus 250 cycles. I can add it up because the whole thing I had operated earlier at 50 megahertz. Now, I am operating this as at 50 megahertz and at 25 megahertz, okay. 25 megahertz means I can now have a supply voltage which is what? Less, okay. And correspondingly, I see that at this supply voltage, my energy per cycle is also much less, not 40. So, if I add these two up, I get 32.5 joule, which is less than definitely 40 joule. So, what I am doing? I am dynamically switching the voltage as well as the frequency. And then if we say that this is the optimal voltage, so what I am doing is, I am doing the entire operation since I have got a deadline, okay, fine. If I have the deadline to operate at that, so I would like to operate at this 4 volts. If I operate completely at 4 volts, then I can do the job in 25 seconds and consuming effectively just 25 joule. So, this becomes optimal. So, what it turns out to be, if you look into it, that to the OS, this scheduling becomes an optimization problem. In fact, if you think in terms of a standard optimization techniques, say integer programming, all these things are applicable here for finding out an optimal schedule of voltage and frequency for doing a task. Okay. So, what is important therefore to note is that this energy management, you need to have support in the hardware, but also your software has to be tuned to exploit these supports to optimally use energy. So, observations therefore are, the minimum energy consumption is achieved for the ideal supply voltage of 4 volts. A variable voltage processor is a processor that allows any supply voltage up to a certain maximum, if we can change it continuously. And it is expensive to support truly variable voltages. Okay. Therefore, actual processors support only a few fixed voltages, and you have to switch between these fixed voltages. Okay. So, some generalizations can be drawn from this is that if a variable voltage processor completes a task before the deadline, the energy consumption can be definitely reduced. So, you are not optimally using the supply voltage and frequency to minimize the energy consumption. The other thing is that if processor uses single supply voltage V and completes a task T just at its deadline, which was a previous case, then V is a unique supply voltage which minimizes the energy consumption of T, okay, because you cannot have anything other than that. Okay. So, in fact, there has been obvious theories with regard to these parameters. So, what we are showing here is that the two aspects, one is we talked about the CPU having different modes, okay, and consuming different amounts of power. CPUs can also provide for different voltages to operate, and corresponding to voltages it would have different frequencies to operate. And it is the job of the operating system or the control software to look at the deadline of the task and then accordingly choose appropriate voltage and the frequency, so that energy consumption is minimum. So, how to do this voltage scaling? The simple approach to do voltage scaling is based on usage model and may not be the current workload, and this approach does not need any OS support. This is the simplest way of doing it. Okay. Another approach is to build the power management policy into the processor's firmware itself. This approach also does not require any modification to the OS. So, depending on a kind of usages that is taking place, okay, you switch to different voltages, okay, as part of the firmware specification. The other thing is that today in your SOCs we have already found there are multi-core architectures, and that is SOCs having heterogeneous processors. And these processors are targeted for doing different kinds of work. So, one of the basic issue involved is match workload to the best processor, and best processor from which point of view? From the point of view of energy consumption. So, it can be according to some objective of energy consumption or even or the energy delay product, which looks at both the parameters together. And this switching here is done by the OS level scheduler at OS time slice multiples. Okay, because in such a case you expect an operating system to run, and the operating system can switch from one processor to another processor. An obvious solution and the most gross solution is if you are not using something, so power down unused core. Okay, so if you are just consider a OMAP processor, and if you are just using basically your OS routines, so you should power down the C55 core and use only the ARM. Another important issue is that if you have a simpler architecture, you have less power consumption. Obviously, more complex architecture means more logic, more switching and more power consumption. So, more complex architecture implies more power consumption. Just look at these pipeline stages. Okay. So, more stages increase register count and the clock load. Okay. Since the register count and the clock load increases, the power consumption is bound to increase. In fact, Pentium 4 uses 22 pipeline stages. Okay. And if we compare ARM 9, which we have studied, uses 5 stage pipeline. Okay. And these figures that we are seeing here, one is 65 watt, another is 0.09 watt. This is not only because of the pipeline, because of the other factors as well, I shall come to it, but pipeline is one of the major factors which reduces the power consumption. So what it is pointing to is that the processors or the processor cores which are targeted for embedded applications will be architecturally much simpler compared to that of your processors targeted for general purpose mainframe computing, because there you have the option to use more sophisticated cooling technology, dissipate the power and have higher power envelopes. Another example is VLIW. Okay. You have got parallel execution units and dependence logic consumes power. Okay. So, this VLIW, although this is used in the context of DSPs, but there also this power consumption becomes an issue. But here the advantage is that if you can do, the other point is very straightforward. Okay, what is the advantage? Advantage is if you can execute multiple instructions in parallel, then the total time taken will be less. So, total energy consumption can be less, although you may consume more power per instruction. Okay. Next thing is speculative branching. Today most of these Pentiums and others, they use speculative branching in hardware. So, what is really speculative branching? That means you try to speculate what would be the next instruction to be executed, you predict and accordingly take actions. Okay. So, this speculation, that is prediction, hardware burns power, and if there are wrong prediction, you actually waste power because of wrong prediction. In fact, this hardware is pretty complex hardware. In fact, if you go back to the Pentium example, what we find is it uses instruction prediction. It predicts which instruction to be executed in future, and accordingly on that basis it tries to prefetch and keep the pipeline full. That prediction process consumes substantial power. Okay, and also it operates at a much higher frequency, and that is why the power consumption is the order of 65 watts. You find on ARM, in that case it does not use prediction, although it uses pipelining, but it does not use instruction prediction. Okay. It is an in order execution, so that prediction logic is not there at all. In fact, you will not find prediction logic in any of these processors which are actually targeted for embedded systems. Okay. And one of the basic reasons for this is this power consumption issue. Also the other reason is use of additional chip area. Now, interesting feature is if you go back and remember that ARM had what? Conditional instructions, and conditional instructions were used to make your pipeline flushing overhead much less. Okay. And that also eliminates the need for a kind of predictive execution to make the optimal utilization of the pipeline. The other thing is, we have already looked at voltage scaling. One point is for the purpose of meeting the deadline. The other thing is that you can also optimize the architecture for energy delay product. We have already seen that energy benefits can be at the expense of performance. Okay. Earlier what we said, that when we are talking about the OS, if you have a deadline, OS would schedule voltages and frequencies such that you are meeting the deadlines. But many of the deadlines for many of these embedded systems are soft deadlines. Let us say a CD player or say a DVD player, they are soft deadlines. And if they are operating on a battery, if I have the battery condition monitoring circuitry in the embedded system, then what can be done? The video rendering, instead of at 20 frames per second, I can reduce it to 30 frames per second. So, really what will happen is your battery life is increased, okay, but you are really are not suffering in terms of performance when it is a soft deadline. Try to understand the basic issue. When it is a deadline you need to meet, then you obviously you try to schedule the voltages and the frequencies such that you meet the deadline and still have power efficiency. But when it is a case of a soft deadline and you really do not have battery power, how can you elongate the lifetime of the battery? Okay. So, you down perform the operation. Okay. That is another strategy which is also used for dealing with this kind of problems. Now, we shall look at memory and cache issues related to the power. So far, we had looked at primarily the processor. So, what is the importance of optimizing memory system energy? Many applications are data intensive, that means your data is in the memory and need to access memory for writing, reading the data. And for embedded systems, some estimate says that memory system can consume up to 90% of the energy. Okay. And system on chip are composed of multiple memories, we have already seen. So, this consumption in the memory is also another source of power drain. It is not only the CPU, so far what we have discussed is primarily the strategies related to the CPU, but memory is also another source of power consumption. So, if you look into this is a general two-dimensional memory architecture. So, you have this bit line, this is a storage RAM cell. So, you have a row decoder, you decode the row, you sense, then you have a read write circuits, then you have a column address, and then you get input output that selects appropriate word from memory row. This is the basic architecture. Why I am showing this basic architecture is, with relation to this architecture you will find how the power consumption is done. So, this is called SRAM, this is the how the power is used. Okay. Now, what has been done is, here it shows the consumptions with relation to different array sizes. Okay. And these different colors indicate that power being consumed in different circuitry. So, it is in decoders, word line, this is bit line, then sense amplifier and the cell, actual cell itself, write circuitry, read circuitry. So, obviously, the maximum power consumption is with respect to this cell itself. Okay. And your write operation is also in many cases power consuming, but your read is in a way much less. So, how do you lower the power this power consumption, let us say in static RAM, because there are different kinds of RAMs, and with respect to that we have to talk about the strategies. The fundamental point is standby power reduction, okay, and then the operating power reduction. Operating power reduction is memory bank partitioning. In fact, this point we had earlier discussed as well, and modifications in the design of the SRAM cell, okay, and maybe combination of the two. Okay. So, in terms of the basic architectural parameter, this memory bank partitioning gives us a pretty optimal strategy. So, what it says is that if we go back to the basic architecture, you partition the memory into smaller banks, so that only the one that is actually accessed is activated. So, the consumption takes place only with respect to this bank. Okay. So, then the corresponding cell that is being made use of and the other circuitry here is leading to much less power consumption, because your lines are not driving all these cells at the same point in time. Okay. So, charging and discharging of capacitors on the lines, and that really is eliminated the moment I go into the smaller banks. So, typically the SRAMs is expected to be organized in terms of this kind of smaller banks to optimize power consumption. So, what are the advantages therefore? Improve speed, because lower bank I can access it faster. Word capacitance is reduced because you are accessing less number of words. Number of activated bit cells is reduced. All these leads to what? Less power consumption, power efficiency. However, the bank decoding circuit adds delay and power, because I have got more decoding circuitry in place. Okay. But these advantages are typically much more compared to that of disadvantages, and so you find that memories are divided to 2 to 8 banks in applications. Next thing is cache. Okay. Cache energy dissipation could be along bit lines. They have to be pre-charged for read and write cycles when they are being executed. Word lines, whenever line is accessed, then you got to have an address decoders. Then you got to have peripheral circuits which actually do the comparators to know really the data is there in the corresponding locations using the tag information and the control logic. So, all these are sources of power consumption in cache. So, how do you go for low power cache techniques? Because cache is implemented primarily using SRAM. So, whatever SRAM techniques I have talked about, they in many cases will translate to here as well. And you can use cache sub-banking, modifications to CAM cell. So, CAM is content accessible memory, which is in many cases used to implement translation look aside buffers. So, we can modify the design to CAM cell to reduce the energy, because that is frequently accessed. There are various other techniques which we shall not discuss in this class that is also used to optimize the power consumption on cache. The cache sub-banking is the simplest way to deal with the problem, okay, in terms of the architectural modification. So, what you have got, your cache is again now organized in terms of sub-banks. Okay. So, this is your sub-bank 1 and this is your sub-bank 0. And at a given point in time, you are doing only one read from one sub-bank and getting the data. So, what you are finding out, the advantages that we had talked and discussed in the context of sub-banking of SRAMs can be used in the context of cache as well. Then what we have is DRAMs, okay, because DRAMs are primarily used for implementation of main memory blocks. Okay. So, conventional DRAMs refresh all rows with fixed single time interval. Okay. Fine. That is the typical DRAM refresh cycle. So, I say that given a DRAM, it has to execute refresh cycles at regular intervals, because the data is stored in the capacitances, the charge is stored in capacitances. So, the charge will decay off. So, I need to refresh so that I can retain the charge. So, typically refresh cycle stalls and read and write accesses, okay, and each refresh cycle would consume power. Now, you cannot really do anything with read and write accesses. Read and write accesses will be required for any kind of program execution and particularly data intensive program execution. But the question is, can I do something with the refresh cycles, okay, by which I can minimize the power consumption. Okay. So, there has been some suggestions and some implementations to take care of this fact. So, one is what is called selective refresh architecture. Okay. Add a valid bit to each row and refresh only those with valid bit set. So, what does that valid bit means? Valid bit means that that bit really has a data. The other things it may have a don't care. So, if it is a don't care, then it is no point refreshing those rows. Classically, when the refresh takes place, this point is not taken into account. You refresh all the rows when the refresh cycle really comes up. So, in this case, you refresh only those rows for which the valid bit is set. In fact, it has been found it can reduce between 50% to 80% refreshes. It depends on how intensively the memory is actually being used. Okay. The other thing is variable refresh architecture. So, data retention time of each cell in this case can be different, because in terms of the technology being used, the data retention time for each cell is different. Add a refresh period table and refresh counter to each row and refresh with appropriate period to each row. Okay. So, that means you are refreshing the rows, but each row gets refreshed with different intervals, because the data retention time of each cell becomes different. Okay. And the other issue is that why it can also become different, it depends on at what point of time you have actually written the data onto that row. Okay. Because your refresh cycles are coming at a regular interval. So, if you have just written the data onto that row, you might not need refresh at that point in time. So, what you are talking about is the refresh cycles with respect to each row, and it reduces about 75% of refreshes. Obviously, this increases the hardware, on chip hardware, but what is the advantage? Advantage is your major power consumption is in refresh cycle, and which is actually in a sense unnecessary consumption, although for retaining of the data, but not related to the computation. Fine. So, you try to minimize the energy consumption there. Next issue is, next most important component is your interconnect, the bus. Okay. And bus is also another source of power consumption, because signals have to flow. In many cases, power supply has to be provided, and if things are connected via wire in a bus, there would be power consumptions in the interconnect. Okay. So, the issue becomes that of dealing with power consumption in the interconnect. In fact, you can have, we had discussed this already, segmented bus and multi-level segmented bus. So, you have the bridges, and with that you can have things connected, and here the component can be connected in either of the buses. So, you have a multi-level segmented bus with the bridge operating in between. Now, obviously, this multi-level segmented bus increases the higher bandwidth, because the whole idea is that the high speed transfer takes place on a smaller bus where it is required, and the low speed devices are connected via bridge. So, effective transfer rate is more. Now, this also saves power, it uses lower power. Why? Because if I got to have a single level bus which has to operate at a higher clock frequency, that means there will be more consumption of power. But many of the devices cannot operate at that frequency, it will introduce wait cycles. But during that period, the consumption of the power is, in a sense, is a wastage. So, if I have buses operating at two different frequencies, two different speeds suited to the devices, then the power consumption becomes different. It is not same for the entire bus onto which the devices are connected. Okay. The other thing, in fact in the last class also we discussed the new trends in the bus architecture is that of having packet switching bus architecture. Okay. So, instead of having direct circuit switching, which is typically which happens in a bus, you have packet switching. So, your packets are getting routed from one point to another point. Okay. So, it obviously offers higher bandwidth, concurrency, because there can be multiple packets being transferred simultaneously, effective spatial reuse of resources, Why? Because if there is a single transfer in terms of a circuit switching, a part of the spatial resources, because the connection between two other elements which are not participating in the transfer does not get utilized. But when it is a packet switching through the router, you can utilize that part of the path as well. Okay. These also becomes power efficient. Why power efficient? Because you are actually making use the bus much more optimally. If the bus resources are getting much more optimally used, okay, your bus traffic is managed better. The moment you manage your bus traffic better, what you have? You have energy efficiency. So, packet switching bus architecture in another way optimizes energy consumption in interconnect. This completes our discussion on this power hour architectural issues. We had looked at processor, memory as well as that of interconnect. And what we have really looked at is basically the hardware issues, hardware design issues, hardware architectural issues. But a very important component is software. How do you write your program such that these features can be efficiently exploited? OS cannot exploit these features if your software is not compatible to exploit these features. In fact, program optimization, one aspect of program optimization for embedded system is that of writing program so that your power consumption is minimized, is not just that of efficiency in execution. Okay. So, this finishes our discussions on power. In the next class, we shall look at features for features which go into architecture and which enable us to do efficient debugging. Any question?
So, are there only discrete values of VDD, like for different times?
Yeah, typically the question you are asking is whether you have discrete values of VDD. If you have continuous value, you have the best efficiency, but it becomes extremely difficult to implement. That is why you get processors with discrete VDD value, and that is what is to be used for optimal energy budget.